I am Briana Williams. I am doing a presentation on logarithms for the class of History of Mathematics. Many people think that mathematics just blossomed into something like a Big Bang theory, but honestly, they are totally wrong. In college, I was able to have the opportunity to take a class called the History of Mathematics. This is where I actually found like significant factors and reasons that mathematics didn't just happen. One plus one didn't just was learned in one day. It was literally created. I also learned from watching a video presentation that one wasn't created first, but actually zero. The history of mathematics and mathematics plays a significant role in our daily, day-to-day work, and such as like the stock market, the banks, just everyday lives of calculations. John Napper was a Scottish man and was the backbone and actually basically created logarithms. Someone else played a part, but we'll get to that in a further video. The mathematician showed tables relating to the powers of two and showed multiplication in one table corresponding to addition in the another. But these tables were not really accepted because the tables had increasingly large gaps and they could not be used for necessary calculations. Napper is also accredited for the first computing machine. He was also the first to describe a systematic use of the decimal point. Other contributions also include formulas used in solving spherical triangles and two formulas known as the Napper analogies. He also stated in one of his books that he published, in computing tables, these large numbers may again be made still larger by placing a period after the number and added ciphers. In numbers, distinguished thus by a period in their midst, whatever is written after the period is a fraction, the denominator of which is unity with as many ciphers after it as there are figures after the point. And that sounds a little complicated right now, but basically Napper was basically also just stating the periods that we use or the decimal point or the that we use to decipher, okay, a whole number, the tenth place or the hundredth place. That's what Napper was in charge of discovering. Not only just logarithms, but the decimal places. Napper also lived during a time where astronomy played a huge role. That was the revolutionary time of calculating the mass of planets, the circulation of the planets, and just the universe in general. Copernicus' theory of the solar system, which is stated that the solar system revolves around on a circle, was published in 1543, and soon astronomers were calculating planetary positions using these ideas. But the 16th century arithmetic was barely up to task, and Napper became interested in this problem. John Kepler was born in 1571 to 1630 near Stuttgart in a modest family. He graduated at the age of 20 from the University of Tübingen, where he studied mathematics and astronomy under Michael Mestel, which was an early supporter of the Copernicus system. In 1594, while engaged in the final year of his studies in theology, he was given the chair of mathematics at Graz, where he became increasingly absorbed in astronomy. He was formally expelled from the town in 1600s on account of his open adherence to the Protestant faith. He came to Prague in 1599 to work as an assistant to Tycho Brahe, and upon Tycho's untimely death in 1601, He inherited his massive stock of accurate planetary observation as well as his job as imperial mathematician to Rudolph II. In 1612, following the downfall of Rudolph II, he moved to Linz in 1621 to and in 1627 to Sag. On the move again because of religious persecution, he fell ill and died 15 November 1630 in Regensburg. Kepler brought the Copernican system to its modern form by replacing Copernicus' circular heliocentric orbit by ellipses with the Sun at one focus, the process through which he arrived at his justly famous law of planetary motion was also often a controlled one, as Kepler peculiar mixture of physical insight and mystical inclinations led him to see causes for the number and arrangement of planetary orbits as opposed to construction purely mathematical descriptions. His first such model involved the nexus of five regular solids and was published in his 1596 Mysterium Cosmographicum. While never relinquishing this idea, in his 1619 Harmonics Mundi, he also sought an explanation in terms of music harmonies. Hidden deep in his work is the first statement of Kepler's so-called third law, establishing the proportionality of the square and planetary orbital periods to the cube of their mean distance to the sun. In 1627, Kepler also published what was to be the crowning but somewhat the, the achievement of planetary motions. These made full of Tycho's store of accurate observations in conjunction with Kepler's new model for planetary orbitations. Josh Brugge was also accredited for discovering logarithms too. He only published maybe a few years after Napler. Josh Brugge is a clock maker from Switzerland and published almost the same thing. He was also known for being a maker of astronomical instruments and a mathematician. His was published in 1620. Now, really, how did logarithms really appear? People did not know how to multiply or even divide numbers. Could you imagine doing that long division all by hand? We would never get done with the test. These calculations were very necessary not only in business but in commerce, but also in astronomy, engineering, and also science. There were calculation centers where people would bring their problem, paying and coming back after a few days to just get the answer. Finally, logarithms do appear. The development of new methods of numerical calculation was a response to the increased practical demands of numerical computations, particularly in trigonometry, navigation, and astronomy. New ideas spread quickly across Europe and resulting by 1630 in a major revolution in numerical practice. Simon Stephen of Holland, in his short pamphlet La Dismay in 1585, introduced decimal fractions to Europe and showed how to extend the principles of Hindu-Arabic arithmetic to calculations with these numbers. Stephen emphasized the utility of decimal arithmetic for all accounts that are encountered in the affairs of men, and he explained in an appendix how it could be applied to survey, stereometric astronomy, and mensuration. His idea was to extend the base 10 positional principle to numbers with fractional parts with a corresponding extension to cover these cases. In his system, the numbers 237.578 was denoted, in which the digits to the left of the zero are the integral part of the number. To the right of the zero are the digits of the fractional part, which digits succeeded by a circular number that indicates the negative power to which 10 is raised. Stevens showed how the usual arithmetic of whole numbers could be extended to decimal fractions, rules that determine the position of negative numbers of 10. Tables of logarithms were first published in 1640 by the Scottish Baron John Napier in his treatise Description of Marvelous Canon of Logarithms. This work was followed 5 years later by another in which Napier set forth the principal use in the construction of his table. The basic idea behind logarithm is that addition and subtraction are easier to perform than multiplication and division, which, as Napier observed, required a tedious expenditure of time and are subject to slippery errors. By the laws of exponents, the multiplication of numbers, the exponents are relatively additively. By correlation, the geometric sequence of numbers a2, A3 is called the base, and arithmetic sequence 1, 2, 3, and the interpolating to fractional values. It is also possible to reduce the problem of multiplication and division to one of an additional and subtraction. To do this, Napier chose a base that would be very close to 1, differ, differ, differing differing from it by only 1 over 1 over 7. The resulting geometric sequence therefore yield a dense set of values suitable for constructing a table. In his work of 1619, Napier presented an interesting kinematic model to generate the geometric and arithmetic sequence used in the construction of his tables. Assume two particles move along separate lines from given initial points. The particles begin moving at the same instant with the same velocity. The first particle continues to move with a speed that is decreasing, proportionate at each instant to the distance remaining between it and given sum at a fixed point on the line. The second particle moves with a constant speed equal to its instant velocity, getting at any increment of time the distance traveled by the first particle in successive increments from a geometrically decreasing sequence. The corresponding distance traveled by the second particle form a arithmetically increasing sequence. Napier was able to use these models to derive theorems yielding precise limits to approximate values into the two sequences. Napier's kinematic models indicated how skilled mathematics had become by the early 17th century and analyzed non-uniformly motion. Kinematic ideas, which appear frequently in mathematics of the period, provided clear and visual means of the generation of geometric magnitude. The concept of a curve traced by a particle moving through space later played a significant role in the development of calculus. Napier's ideas were taken up and revised by the English mathematician Henry Briggs, the first Sabine Professor of Geometry at Oxford. In 1624, Briggs published an extensive table of common logarithms or logarithms to the base 10. Because the base was no longer close to 1, the table could not be obtained as simply as Napier's and Briggs. Therefore, devised techniques involved the calculus of finite differences to facilitate calculation of the entries. He also devised interpolation procedures of great computation efficiency to obtain intermediate values. In Switzerland, the instrument maker Jos Buger arrived at the idea for logarithm independently of Napier, although he did not publish the results in 1620. 4 years later, a table of logarithms prepared by Johannes Kepler appeared in Marburger. Both Virga and Kepler were astronomical observers, and Kepler included logarithm tables in his famous Rudolph tables. Astronomical tribulations of planetary motion derived using the assumption of elliptical orbits around the sun. So how do logarithms really work? Logarithms are based on exponential functions. Common laws are based on a 10 raised to a power. so x equals 10 to the y. Natural laws, which are based on the numbers e raised to a power, are used mostly in higher and theoretical mathematics, which is x equals e to the y power. Either of these functions can be graphed in a normal way and produce the typical exponential curve. Notice how x and y are interchanged in these expressions. To write logarithmic notations, we use log subscript x or log subscript ax. This is where log base a of x, and also y equals log subscript x means x equals a superscript y, and so a logarithm is simply an exponent of some base. To show an inverse relation in its function, we show an inverse function using the notation f of x superscript -1. A function is inverted by interchanging the x and y values, then resolving for y. Inverting a function reflects it across the line, as shown in the graph to the left. So to just go over a brief overview of logarithms and what it is and what do they do. Remember these key points. Logarithms are a mathematical tool originally invented to reduce arithmetic computations. Multiplication and division are reduced to simple addition and subtraction. Exponential and root operations are reduced more simple exponent multiplication or division. Changing the base of numbers is simplified. Scientific and graphing calculators provide logarithmic function for base 10, which is common, and base e, which is natural logs. Both log types can be used for ordinary calculations. So the law of exponents and logarithms include law for multiplication is b superscript times b y superscript equals b superscript x plus y. Law for division is b superscript divided by b superscript y equals, you would b superscript x minus y. Law for power of a power is b superscript x superscript y equals b superscript x times y. Law for negative exponents is b minus negative x superscript equals 1 divided by b superscript. Exponential functions always have the variable in their exponent. For f of x equals 2x is an exponential function. F of x equals x squared is not an exponential function. The reason being is that the definition describes the function f of x equals ax, where a is a positive number, which 2 is a positive number. Constant other than 1 is called an exponential function base a. x2 is not an exponential function because a, which is represented by x, is not a positive number other than 1. Conversation between log and exponential form is often a convenient way to solve problems. Exhibit A, because x equals ay and y equals log ax are equivalent, then 2 exponential ax equals a is the same as x equals log subscript a. Log problems are solved the same way. Log 2x equals -3, the equivalent of 2 superscript or power of -3. And by the laws of exponents, we obtain x equals 1/2 third to the third power, or x equals 1/8. Properties of logarithmic functions. We always assume that a positive 1 and is a constant, so it can serve as a logarithm base. This is a proof of the first theorem of logarithms. The proof is as follows. For any positive number x and y, log a of x and y equals log ax plus log a y. Let b equals log ax and c equal log a y. This is equivalent to x equals ab and y equals ac. Now multiply x and y. Xy equals a to the b power a to the c power, or by a law of exponents equals a to the exponent b plus c. As a logarithmic statement, we can now write log a xy equals b plus c. In replacing the values of b and c, our solution is log a xy equals log a x plus log a y. Some additional log computations shows these theorems. Log ax to the p power equals p times log ax. This is raising a number to a power by multiplying the log of the number, taking the root of a number by dividing the log of that number. The second theorem shows log ax divided by y. You would complete this by log ax minus log ay. You simply just divide two numbers by subtracting the logs of the two numbers. The third one and final one is log b n, which is the natural number, which has its own number, equals log a n divided by log a b. Change the base number n by dividing its log by the log of the new base. So how do we use logarithms? Logarithm calculation produces answers as an exponent. To find the actual numeric solution of the calculation, the anti-logarithm of the result must be found. When using this is done by raising the base number to the power of the exponent. Example, using common logs, find the value of 37 to the third power. Step 1. Using calculator, find the common logarithm of 37 and 1.58201,724. Then multiply that by 3 of 4.704605172. Step 2. Use a calculator to find the value of 10 to the 4.704605172. The answer you will get is 50,653. In conclusion, we learned logarithms were originally devised to simplify arithmetic. Logarithms are simply exponents of some base of base of 10 and therefore follow all the rules of exponential powers. Logarithms can be used any base, but only two bases are normally used today. Common logs use a base of 10 and natural logs use ease of their base. The modern calculator has really just eliminated the need or use of logarithms in ordinary calculations. We also learned that Kepler and Bugatti was the main components of generating the foundations of logarithms, even though they're not using the same calculations of the ancient mathematics, they still played a major part for today's creations. Thank you.